Welcome, dear listener, to this gentle journey through the magnificent forces that shape our atmosphere. Tonight, we will explore the wonder of extreme weather, not with alarm, but with curiosity and calm. Let the rhythm of these natural processes guide you toward rest as we discover together how the air around us transforms, how energy moves through invisible currents, and how the sky itself becomes a canvas for some of nature's most powerful artistry. As you settle into comfort, allow your breathing to slow and deepen. There is no urgency here, no need to grasp or hold on to every detail. Simply let the words wash over you like a gentle rain. And if your mind begins to wander towards sleep, that is perfectly natural. We are here to explore the atmosphere's rhythms, and in doing so, perhaps find our own inner calm reflected in these vast meteorological cycles. The air around us is never truly still. Even in moments of apparent quiet, molecules dance and drift, responding to subtle differences in temperature and pressure that our senses cannot detect. The atmosphere is a fluid ocean, three-dimensional and ever-moving, stretching from the ground beneath our feet to the edge of space itself. Within this ocean, weather is born, not randomly, but through elegant physical processes that have operated for billions of years, long before humans walked the earth to witness them. Tonight's journey will take us from the gentlest beginnings of atmospheric change through increasingly dramatic transformations. We will witness how a simple difference in temperature can cascade into thunderstorms, how the ocean's warmth can birth hurricanes, how rotating air can tighten into tornadoes. But we will approach these phenomena not as threats to fear, but as natural expressions of our planet's energy balance. The atmosphere's way of redistributing heat, moisture, and momentum across the globe. Let your body sink deeper into whatever supports you now. Feel the weight of your limbs, the softness of your breath. As we explore these weather patterns together, you might notice your own inner weather, thoughts that drift like clouds, emotions that shift like winds. All of this is natural. All of this is welcome. And all of it, like the weather itself, will pass and change and transform. The foundation of all weather, extreme or gentle, lies in a simple truth. Our planet receives uneven heating from the sun. The equator, where sunlight strikes most directly, absorbs tremendous energy throughout the year. The poles, where light arrives at a shallow angle, receive far less. This imbalance creates a fundamental restlessness in the atmosphere, a need to move heat from warm regions to cool ones, to balance what the sun has made unbalanced. If Earth did not rotate, if it had no oceans, if its surface were perfectly uniform, this heat transfer might occur through simple, predictable circulation patterns. Warm air would rise at the equator, flow toward the poles at a high altitude, sink in the polar regions, and return along the surface. But our planet is far more complex, far more interesting. It spins, creating the Coriolis effect that deflects moving air. It holds vast oceans that store and release heat differently than land. It bears mountains that force air upward, valleys that channel winds, forests and deserts and ice sheets that each interact uniquely with the atmosphere above them. From this complexity emerges the rich tapestry of weather we experience, the gentle breeze and the howling gale, the light shower and the torrential downpour, the fair weather cumulus cloud and the towering thunderstorm. Each represents the atmosphere's ongoing effort to achieve balance, to smooth out differences in temperature and pressure and moisture. Extreme weather, in this sense, is simply the atmosphere working with particular intensity, moving energy with exceptional speed and power. Consider for a moment the invisible architecture of the atmosphere itself. We live at the bottom of an ocean of air, in the layer called the troposphere, where virtually all weather occurs. This layer extends upward about 7 miles at the poles and 11 miles at the equator, a thin skin on our planet, yet containing all the winds and clouds and storms we will ever experience. Above it lies the stratosphere, calmer and more stable, where the ozone layer absorbs ultraviolet radiation. Higher still are the mesosphere and thermosphere, growing thinner and thinner until air gradually gives way to the vacuum of space. But it is here, in the troposphere, where the drama unfolds. Here, temperature generally decreases with altitude, a crucial fact that allows air to rise and clouds to form. Here, water exists in all 3 phases: invisible vapor, liquid droplets, solid ice crystals. Here, the sun's energy drives an endless cycle of evaporation and condensation, heating and cooling, rising and sinking. Let us begin our exploration with the gentlest precursors of extreme weather, the subtle signs that appear long before any storm, the quiet gathering of ingredients that will later combine into something powerful. On a calm morning, you might step outside and notice nothing remarkable. The sky might be clear, or perhaps dotted with fair weather cumulus clouds, those puffy, white, flat-bottomed clouds that drift lazily across blue skies. These clouds form when the sun heats the ground, which in turn heats the air just above it. Warm air is less dense than cool air, and so it begins to rise, like a bubble released underwater. As this air rises, it expands, because atmospheric pressure decreases with altitude, and as it expands, it cools, following a principle of physics as reliable as gravity itself. For every 1,000 feet of altitude gained, rising air cools up about 5.5 degrees Fahrenheit if it is unsaturated, that is, if it has not yet reached the point where its water vapor begins to condense. This rising, expanding, cooling air eventually reaches a level where it can no longer hold all its water vapor. The air becomes saturated and condensation begins. Water vapor, invisible gas, transforms into tiny liquid droplets or ice crystals, each one microscopic, yet collectively visible as a cloud. This transformation releases heat, because condensation is the opposite of evaporation, and evaporation requires energy. The released heat warms the air slightly, making it more buoyant, encouraging it to rise even further. This is how a cumulus cloud is born, from sunshine warming the ground, from air rising and cooling, from water vapor condensing into visibility. On a stable day, these clouds remain small and scattered. They rise to a certain level, spread out slightly, and then dissipate as the air within them mixes with drier surrounding air. They are beautiful, easeful, the very image of a pleasant day. But sometimes conditions are different. Sometimes the atmosphere is unstable, meaning that rising air, even after cooling, remains warmer than its surroundings. In such conditions, the air continues to rise, accelerating upward, building taller and taller clouds. The flat-bottomed cumulus begins to tower, growing into cumulus congestus, then potentially into cumulonimbus, the thunderstorm cloud, the anvil-headed giant that can reach the stratosphere itself. This transformation from fair weather cloud to storm cloud does not happen instantly. It requires specific ingredients, each one necessary, each one contributing to the eventual outcome. Let us explore these ingredients with the same patience the atmosphere shows as it gathers them together. First, there must be moisture, water vapor in the air. This moisture typically comes from evaporation from oceans, lakes, rivers, soil, and vegetation. A single large tree can release hundreds of gallons of water vapor into the atmosphere each day through transpiration. Multiply this by the billions of trees in a forest, add the evaporation from nearby water bodies, and you begin to understand how the air can become laden with moisture, especially in warm seasons and tropical regions. Second, there must be instability, an atmospheric profile where temperature decreases rapidly with altitude, making the air prone to vertical motion. Instability often develops when the sun heats the ground intensely, creating a layer of very warm air near the surface, while cooler air remains aloft. Alternatively, instability can develop when cool air moves in at upper levels, increasing the temperature contrast. Meteorologists measure instability using various indices, but the fundamental concept is simple. Unstable air wants to move vertically, like oil trying to rise through water. Third, there must be lift, some mechanism to start air rising in the first place. This might be surface heating, as we have discussed, creating thermals that bubble upward. It might be a front, where two air masses of different temperatures collide, forcing the warmer, lighter air to rise over the cooler, denser air. It might be a mountain range, forcing air to ascend its slopes. It might be convergence, where winds from different directions meet, and having nowhere else to go, push air upward. Each of these lifting mechanisms can trigger cloud development if the other ingredients are present. Fourth, and often crucial for the most severe weather, there must be wind shear, a change in wind speed or direction with altitude. Wind shear might seem like it would disrupt storm development, and indeed, too much shear in the wrong configuration can tear a developing storm apart. But the right kind of wind shear actually organizes storms, allowing them to persist for hours instead of minutes, and enabling them to rotate, which can lead to tornadoes. As you listen to these ingredients being described, you might notice your own breathing, your own body's gentle rhythms. Just as the atmosphere requires multiple factors to align for extreme weather, your body and mind require certain conditions for deep rest. Comfort, quiet, darkness, a sense of safety. Easy ingredients for sleep, and they are gathering now, slowly, naturally, like moisture accumulating in the morning air. Let's imagine we are observing a day when all these ingredients are coming together. It is late spring in the central United States, a region where extreme weather is particularly common due to the unique geography and atmospheric patterns. The morning begins quietly. The sun rises over the Great Plains, that vast expanse of relatively flat land stretching from the Rocky Mountains eastward to the Mississippi River Valley. As sunlight strikes the ground, the earth begins to warm, but not uniformly. Bare soil heats faster than vegetated areas, urban surfaces faster than rural ones, south-facing slopes faster than north-facing ones. These differences create a patchwork of temperatures across the landscape, and above each warmer patch, air begins to rise. If you could see the invisible thermals, the atmosphere would appear to be bubbling, with columns of rising air scattered across the region like invisible pillars connecting earth to sky. By mid-morning, the first cumulus clouds appear, marking the tops of these thermals. They are small at first, perhaps only a few hundred feet thick, lasting only minutes before evaporating. But as the day progresses and the ground continues to heat, the thermals grow stronger, the clouds grow larger, and some begin to persist rather than immediately dissipating. Meanwhile, in the upper atmosphere, something else is happening. A jet stream, a river of fast-moving air, at altitudes around 30,000 feet, is approaching from the west. Jet streams form along boundaries between air masses of very different temperatures, and they play a crucial role in weather development. This particular jet stream is bringing cooler air aloft, increasing the instability. It is also creating wind shear, as winds at the surface blow from the south or southeast, bringing warm, moist air from the Gulf of Mexico, while winds aloft blow from the west or southwest at much higher speeds. By early afternoon, the atmosphere is primed. The surface air is warm and humid. Having absorbed heat from the ground and moisture from the Gulf, the air aloft is cooler and drier. The temperature profile is steep, meaning temperature decreases rapidly with altitude, creating strong instability. Wind shear is present, with winds changing direction and speed from the surface to the upper troposphere. All that is needed now is a trigger, a focus for storm development. That trigger might come in the form of a front, perhaps a cold front, advancing from the northwest, a boundary between the warm, moist air mass and a cooler, drier one. Along this front, the cooler air acts like a wedge, sliding under the warmer air and forcing it upward. Or the trigger might be a dry line, a boundary between moist air from the Gulf and dry air from the desert southwest, common in the southern plains. Or it might simply be that the daytime heating has become so intense that thermals finally break through any stable layers that had been capping them, like a lid finally lifting off a boiling pot. Whatever the trigger, once air begins rising in earnest through this unstable atmosphere, the process accelerates. The rising air cools, and its water vapor condenses, forming cloud droplets and releasing latent heat. This heat makes the air even more buoyant, causing it to rise faster. As it rises faster, it draws in more air from below, creating an updraft, column of rising air that can reach speeds of 60 miles per hour or more in a strong thunderstorm. The cloud grows rapidly now, transforming from cumulus to towering cumulus to cumulonimbus in perhaps 30 minutes. Its top, initially rounded and cauliflower-like, begins to glaciate, meaning the water droplets freeze into ice crystals as they reach altitudes where temperatures are well below freezing. The cloud takes on a harder, more fibrous appearance at its top. It continues rising, sometimes reaching 40,000 feet or higher, until it encounters the tropopause, the boundary between the troposphere and stratosphere. At the tropopause, the temperature profile changes. In the stratosphere, temperature increases with altitude rather than decreasing, creating a stable layer that acts like a ceiling. The rising air, having reached this level, can rise no further. Instead, it spreads out horizontally, creating the characteristic anvil shape of a mature cumulonimbus cloud. This anvil can extend for miles downwind, a vast shield of ice crystals that may persist long after the storm itself has dissipated. Let your mind rest for a moment in this image, a towering cloud brilliant white in the sunshine, its top spreading into an anvil against the deep blue of the upper atmosphere. There is something majestic about such a cloud, something that inspires both awe and a certain peaceful acceptance of nature's power. You are safe here, observing from a distance, learning about these processes without any need for concern. Inside this developing thunderstorm, the atmosphere is anything but peaceful. The updraft continues to strengthen, drawing in air from the surrounding environment. This inflow can be felt at the surface as winds that increase and shift direction, blowing toward the storm. The updraft carries water droplets and ice crystals upward, and some of these particles grow large enough that the updraft can no longer support them. They begin to fall, creating a downdraft, a column of sinking air. This downdraft is crucial to the storm's structure and evolution. As precipitation falls through the cloud, it drags air downward with it. This descending air brings cooler temperatures from aloft down to the surface. When the downdraft reaches the ground, it spreads out horizontally, creating gusty winds and a noticeable temperature drop. If you have ever experienced the sudden cool breeze and wind shift that precedes a thunderstorm's arrival, you have felt the downdraft's outflow. The boundary between this cool outflow and the warm air it is displacing is called a gust front, and it acts like a miniature cold front, lifting the warm air and potentially triggering new updrafts. In this way, a thunderstorm can be self-sustaining for a time, with its own outflow helping to maintain the inflow that feeds the updraft. But there is a problem with this arrangement. If the downdraft and its cool outflow spread directly beneath the updraft, they can cut off the storm's supply of warm, moist inflow air. The updraft weakens, precipitation decreases, and the storm begins to dissipate. This is the fate of most ordinary thunderstorms. They last perhaps 30 to 60 minutes before their own downdraft undermines them. However, when wind shear is present, something different can happen. The shear, the change in wind with altitude, tilts the updraft so that it does not rise vertically, but at an angle. This means the downdraft and its outflow occur in a different location from where the updraft is drawing in air. The storm becomes organized with distinct regions for inflow, updraft, precipitation, and outflow. Such a storm can persist for hours, traveling across the landscape, producing heavy rain, frequent lightning, strong winds, and possibly hail or tornadoes. These long-lived, organized thunderstorms are called supercells, and they represent some of the most intense weather phenomena on Earth. Before we explore supercells and their offspring in detail, let us pause and consider the lightning that illuminates these storms, one of nature's most spectacular displays, and a phenomenon that has fascinated and frightened humans throughout history. Take a slow, deep breath, hold it gently for a moment, then release it, feeling any tension flow out with the exhale. We are going to explore lightning now, but we will do so with curiosity rather than fear, understanding the physics that creates these brilliant flashes. Lightning is fundamentally an electrical phenomenon, a giant spark that bridges the gap between regions of opposite electrical charge. To understand how lightning forms, we need to understand how thunderstorms become electrically charged in the first place, a process that scientists have studied for decades and still do not completely understand in all its details. The prevailing theory involves the collision of ice particles within the thunderstorm cloud. In the mixed phase region of the cloud, where temperatures are below freezing, but liquid water droplets still exist, alongside ice crystals, collisions occur constantly. Smaller ice crystals, carried upward by the updraft, collide with larger grippled particles, soft hail, that are falling or suspended in the updraft. During these collisions, charge is transferred, with the smaller ice crystals typically becoming positively charged and the larger grapple becoming negatively charged. The updraft carries the small, positively charged ice crystals to the upper regions of the cloud, while the larger, negatively charged grapple remains in the middle and lower regions. This separation of charge creates an electrical field within the cloud. Positive charge accumulating near the top, negative charge in the middle, and often a smaller region of positive charge at the very bottom. As the storm continues to develop, this charge separation intensifies. The electrical field grows stronger and stronger until it reaches a critical threshold, typically around 3 million volts per meter. At this point, the insulating properties of air break down, and a lightning flash occurs. Most lightning, about 75%, occurs within the cloud itself or between clouds, as charge flows from one region to another. These intra-cloud or cloud-to-cloud flashes illuminate the storm from within, creating the sheet lightning that makes the entire cloud glow. But the lightning that captures our attention most dramatically is cloud-to-ground lightning, where the electrical discharge bridges the gap between cloud and earth. Cloud-to-ground lightning begins with a stepped leader, a channel of ionized air that propagates downward from the cloud in a series of steps, each about 50 meters long, occurring so rapidly that the eye cannot distinguish them. This leader is invisible or barely visible, branching as it descends, seeking the path of least resistance towards the ground. It carries negative charge downward, and as it approaches the ground, it induces positive charge in the earth below, particularly in tall objects like trees, buildings, and towers. When the specked leader gets close to the ground, typically within 100 meters or so, the electrical field becomes so intense that one or more upward streamers launch from the ground, reaching up to meet the descending leader. When leader and streamer connect, a conductive channel is established between cloud and ground. What happens next occurs almost instantaneously. Negative charge from the cloud rushes down this channel to the ground, but more visibly, positive charge surges upward from the ground in what is called the return stroke. This return stroke is what we see as the bright flash of lightning, a channel of air heated to approximately 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. This extreme heating causes the air to expand explosively, creating the shock wave we hear as thunder. The entire process, from stepped leader to return stroke, takes only a few milliseconds. But often, lightning does not end with a single stroke. Additional leaders, called product leaders, can travel down the same ionized channel, followed by additional return strokes. A single lightning flash may contain 3 or 4 strokes, sometimes more, occurring so rapidly that they appear as a single flickering flash to the human eye. Thunder, the acoustic signature of lightning, provides information about the distance and extent of the flash. Sound travels through air at approximately 1 mile every 5 seconds. So by counting the seconds between seeing lightning and hearing thunder, you can estimate the distance in miles. A 3-second delay means the lightning was about 3/5 of a mile away. Thunder from very distant lightning may not be audible at all, as sound waves dissipate and are absorbed by the atmosphere. Lightning visible, but too distant to hear, is sometimes called heat lightning, though it is simply ordinary lightning from a distant storm. The sound of thunder itself varies depending on your distance from the lightning channel. Nearby lightning produces a sharp crack or bang as the shock wave reaches you with little distortion. More distant, lightning creates a rumble as sound waves from different parts of the lightning channel arrive at different times and as they reflect off clouds, terrain, and buildings. Very close lightning, within a few hundred feet, can produce thunder so loud and sudden that it is physically startling, a visceral reminder of the energy involved. Let us rest here for a moment, in the space between lightning and thunder. Imagine you are watching a distant storm from a safe, comfortable place, perhaps through a window or from a covered porch. The storm is far enough away that there is no danger, close enough that you can see the lightning illuminate the clouds from within, and occasionally see a bolt reach from cloud to ground. Several seconds after each flash, the thunder arrives, a low rumble that you feel as much as hear. There is something deeply primal about this experience, something that connects us to countless generations of humans who watched storms and wondered at their power. Your breathing has perhaps slowed as you have listened to this description. Your body is growing heavier, more relaxed. The storm we are imagining is moving away now, the lightning becoming less frequent, the thunder more distant. Soon it will be gone entirely, leaving only the memory of its passage and the fresh, clean smell of rain-washed air. But our exploration continues because we have only begun to understand the full spectrum of extreme weather. The thunderstorm we have been observing, impressive as it is, represents just one manifestation of atmospheric instability. When conditions align in particular ways, thunderstorms can organize into larger systems or intensify into supercells or cluster along fronts to create squall lines that persist for hundreds of miles. Consider the supercell thunderstorm, the king of thunderstorms, the most intense and long-lived of all convective storms. Supercells are relatively rare, requiring specific conditions to form, but when they do develop, they are capable of producing the most severe weather, giant hail, damaging winds exceeding 80 miles per hour, and the strongest tornadoes. What distinguishes a supercell from an ordinary thunderstorm is rotation. A supercell contains a rotating updraft, called a mesocyclone, typically several miles in diameter, that can persist for hours. This rotation develops through the interaction of the updraft with wind shear, specifically with the type of wind shear where wind speed increases with altitude and wind direction changes with altitude, a profile called speed and directional shear. Imagine a horizontal tube of air rotating around a horizontal axis due to wind shear. Faster winds aloft, slower winds below. Now imagine the thunderstorm's updraft encountering this horizontal rotation. The updraft tilts the rotating tube into a vertical orientation, creating a vertically rotating column of air within the storm. This is the mesocyclone, and its presence fundamentally changes the storm's behavior. The mesocyclone acts like a chimney, efficiently ventilating the storm by removing air from the updraft region and allowing more air to flow in at low levels. This makes the updraft stronger and more persistent than it would be in a non-rotating storm. The rotation also helps to separate the updraft from the downdraft, preventing the storm from cutting off its own inflow. As a result, supercells can maintain their intensity for many hours, sometimes traveling hundreds of miles across the landscape. Within a supercell, The updraft can reach extraordinary speeds, 100 miles per hour or more. Such an updraft can suspend large hailstones, allowing them to grow to impressive sizes. Hail forms when water droplets are carried upward into the freezing levels of the cloud and they freeze into ice. If the updraft is strong enough, these ice particles are carried repeatedly through regions of supercooled water, liquid water that exists below freezing temperature, allowing layer after layer of ice to accumulate, like an onion growing new layers. Eventually, the hailstone becomes too heavy even for the powerful updraft to support, and it falls to the ground. In strong supercells, hailstones can reach the size of golf balls, ace balls, or even softballs. The largest hailstone ever recorded in the United States fell in Vivian, South Dakota, in 2010, measuring 8 inches in diameter and weighing nearly 2 pounds. Such a hailstone, falling from perhaps 40,000 feet at terminal velocity, carries tremendous kinetic energy, enough to shatter windows, dent cars, damage roofs, and injure or kill livestock, and rarely people. But perhaps the most feared product of supercell thunderstorms is the tornado, a violently rotating column of air extending from the cloud base to the ground. Not all supercells produce tornadoes. In fact, only about 20 to 30% do. But supercells account for nearly all strong and violent tornadoes, those rated EF2 or higher on the enhanced Fujita scale. We will explore tornadoes in greater depth shortly, but for now, let us simply acknowledge them as part of the supercell's repertoire, one more way that atmospheric rotation and instability can manifest in extreme form. As you continue to relax, to let the descriptions wash over you like waves on a shore, you might notice that your awareness is becoming softer, less focused. This is natural. You do not need to remember every detail, every fact. The purpose of this journey is not to memorize, but to experience, to let the rhythms of atmospheric processes guide you toward rest. Let us shift our attention now from the individual thunderstorm to larger-scale organizations of storms. Under certain conditions, thunderstorms do not remain isolated, but instead organize into lines or clusters that can persist for many hours and affect areas hundreds of miles across. One common organization is the squall line, a line of thunderstorms, sometimes hundreds of miles long, that advances across the landscape like a wave. Squall lines typically form along or ahead of cold fronts, where the advancing cool air forces warm, moist air upward along an extended boundary. The resulting line of storms can produce a continuous swath of heavy rain, frequent lightning, and strong winds. The leading edge of a squall line is often marked by a shelf cloud, a low horizontal cloud that extends outward from the main storm, like a shelf or ledge. This cloud forms as the storm's cool outflow lifts the warm air ahead of it, causing condensation. Beneath the shelf cloud, winds can be strong and gusty, and the temperature drops noticeably as the outflow passes. Then comes the rain, often heavy, sometimes accompanied by small hail and frequent lightning. Behind the leading line of storms, additional cells may develop, creating a stratiform rain region, an area of lighter but more persistent precipitation that can last for hours. This stratiform region forms as the storm's anvil cloud, that vast shield of ice crystals at high altitude, gradually descends and produces rain. The total rainfall from a squall line, the heavy rain from the leading convective line, plus the lighter rain from the trailing stratiform region, can be substantial, sometimes leading to flash flooding. Another organization pattern is the mesoscale convective system, or MCS, a complex of thunderstorms that becomes organized on a scale larger than individual storms, but smaller than typical weather systems like fronts. NCSs can take various forms, but one of the most impressive is the mesoscale convective complex, or 1200, a roughly circular cluster of thunderstorms that can span an area the size of Iowa. Multiplies typically develop in the evening and reach peak intensity during the night, persisting until morning. They form when individual thunderstorms merge and organize, their cold outflows interacting to create new updrafts, their anvils spreading and merging into a vast cloud shield. From satellite, and 1200 appears as a nearly circular area of very cold cloud tops, indicating deep convection and heavy precipitation. These systems are important rain producers, especially in the central United States during summer. A single 1200 can drop several inches of rain over a large area, replenishing soil moisture and filling reservoirs. But they can also produce flooding, particularly if they move slowly or repeatedly affect the same area. As you listen to these descriptions for organized storm systems, you might imagine viewing them from space, from the perspective of a weather satellite. From that vantage point, the storms appear as swirls and patterns of white against the darker earth and ocean, beautiful and abstract, their violence and intensity reduced to shapes and textures. There is something calming about this perspective, this reminder that even the most intense weather is, from a sufficient distance, simply pattern and process, the atmosphere doing what it has always done. Let your eyes grow heavy now, if they have not already. Let your body sink deeper into rest. We are going to continue our journey, moving from the thunderstorms of the mid-latitudes to the tropical cyclones of the warm oceans, hurricanes, typhoons, and cyclones, different names for the same phenomenon, the largest and most powerful storms on Earth. But first, let us pause. Let us simply rest in silence for a few moments, allowing the information to settle, allowing your mind to drift where it will. There is no hurry. The atmosphere has been creating storms for billions of years, and it will continue long after we are gone. We are simply observers, learning and wondering, and gradually, gently, falling towards sleep. Hold this quiet space. Breathe slowly. Notice the stillness around you, the comfort of your resting place. Notice how your body feels, perhaps heavy, perhaps warm, perhaps simply neutral and at ease. This is good. This is exactly as it should be. Now, let us continue, moving our attention to the tropics, to the warm waters, where the ocean and atmosphere exchange energy on a vast scale, and where that energy can organize into the rotating storms we call tropical cyclones. Tropical cyclones are heat engines, machines that convert the thermal energy of warm ocean water into the kinetic energy of wind. They require very specific conditions to form, which is why they occur only in certain regions and only during certain seasons. Understanding these requirements helps us appreciate both the power of these storms and their place in the global climate system. First, tropical cyclones require warm ocean water, typically at least 80 degrees Fahrenheit, and not just at the surface, but to a depth of at least 150 feet. This warm water provides the energy for the storm through evaporation. As water evaporates from the ocean surface, it carries latent heat into the atmosphere. When this water vapor later condenses into clouds and rain, the latent heat is released, warming the air and making it more buoyant, driving the storm's circulation. Second, tropical cyclones require low wind shear, unlike mid-latitude thunderstorms, which can benefit from wind shear. Tropical cyclones are disrupted by it. Strong wind shear can tilt the storm's circulation, separating the upper-level outflow from the lower-level inflow and preventing the storm from organizing. This is why tropical cyclones form primarily in the tropics during summer and early fall, when wind shear is typically weak. Third, tropical cyclones require sufficient distance from the equator, typically at least 5 degrees of latitude. This is because the Coriolis effect, which causes moving air to deflect to the right in the northern hemisphere and to the left in the southern hemisphere, is necessary to initiate and maintain rotation. At the equator itself, the Coriolis effect is zero, so tropical cyclones cannot form there. Fourth, tropical cyclones require a pre-existing disturbance, some initial area of low pressure, and organized thunderstorms that can serve as a seed for development. In the Atlantic, these disturbances often originate as tropical waves, ripples in the atmospheric flow that move westward off the coast of Africa. Most tropical waves do not develop into tropical cyclones, but a few, encountering favorable conditions, begin to organize and intensify. When conditions are right, the process of tropical cyclone formation, called tropical cyclogenesis, unfolds over several days. The initial disturbance produces thunderstorms, which release latent heat, which warms the air, which lowers the surface pressure, which causes air to converge and rise, which produces more thunderstorms. This positive feedback loop gradually intensifies the system. As surface pressure falls, winds increase, flowing inward toward the low-pressure center. The Coriolis effect deflects these winds, causing them to spiral rather than flowing directly inward. The system begins to rotate, slowly at first, and more rapidly as it intensifies. The thunderstorms become more organized, arranging themselves in spiral bands around the center. If intensification continues, the system progresses through a series of classifications based on wind speed. It begins as a tropical disturbance, then becomes a tropical depression when sustained winds reach 23 miles per hour. When winds reach 39 miles per hour, it becomes a tropical storm and receives a name. And when winds reach 74 miles per hour, it becomes a hurricane, or a typhoon in the western Pacific, or a cyclone in the Indian Ocean, different names for the same phenomenon. As a tropical cyclone intensifies, its structure becomes more defined. The strongest winds and heaviest rain occur in the eye wall, a ring of intense thunderstorms surrounding the center. The eye wall is where air is rising most rapidly, where latent heat release is greatest, where the storm's circulation is strongest. Inside the eye wall is the eye, a region of calm, where air is sinking, clouds are few, and winds are light. The eye typically ranges from 10 to 40 miles in diameter, though it can be smaller in very intense storms or larger in weaker ones. The contrast between the violence of the eye wall and the calm of the eye is one of the most remarkable features of tropical cyclones. People who have experienced the passage of a hurricane's eye describe an eerie calm with clear or partly cloudy skies, light winds, and sometimes even sunshine sandwiched between the two passages of the eye wall. This calm is temporary, lasting perhaps 30 minutes to an hour before the back side of the eye wall arrives, with winds from the opposite direction. Surrounding the eye wall are rain bands, spiral bands of thunderstorms that curve outward from the center, like the arms of a spiral galaxy. These rain bands extend hundreds of miles from the center, bringing gusty winds and heavy rain to areas far from the eye. Between the rain bands are relatively calmer areas, with lighter rain or no rain at all, so the passage of a tropical cyclone is often characterized by alternating periods of intense and lighter weather as successive rain bands move through. The size of tropical cyclones varies considerably. Some are compact, with hurricane-force winds extending only 20 or 30 miles from the center. Others are vast, with hurricane-force winds extending more than 100 miles from the center, and tropical storm-force winds extending 300 miles or more. Hurricane Sandy in 2012, though not exceptionally intense in terms of wind speed, was enormous in size, with tropical storm-force winds extending nearly 1,000 miles in diameter at one point. The intensity of tropical cyclones is measured by their maximum sustained winds, and they are categorized using the Saffir-Simpson hurricane wind scale. Category 1 hurricanes have winds of 74 and 95 miles per hour and can cause some damage, primarily to trees, power lines, and poorly constructed structures. Category 2 hurricanes have winds of 96 to 110 miles per hour and cause more extensive damage. Category 3, 4 and 5 hurricanes, with winds of 111 miles per hour or greater, are considered major hurricanes capable of causing devastating to catastrophic damage. The strongest tropical cyclones on record have had sustained winds exceeding 190 miles per hour, with gusts even higher. Typhoon Haiyan, which struck the Philippines in 2013, had sustained winds estimated at 195 miles per hour at landfall, making it one of the strongest tropical cyclones ever recorded at landfall. The destruction was immense, with entire communities leveled by the combination of wind and storm surge. Storm surge, the abnormal rise in water level caused by a tropical cyclone, is often the deadliest aspect of these storms. As the storm approaches the coast, its winds push water toward the shore, and the low pressure at the storm center allows water to rise higher than it would otherwise. The result is a dome of water that can be 20 feet high or more in the most intense storms, inundating coastal areas and causing catastrophic flooding. The shape of the coastline and the offshore bathymetry, the underwater topography, strongly influence storm surge height. Bays and estuaries can funnel and amplify the surge, while gradually sloping offshore terrain allows the surge to build higher than it would over steeply sloping terrain. Hurricane Katrina in 2005 produced a storm surge of nearly 30 feet in some locations along the Mississippi coast, while Hurricane Ike in 2008 produced a surge of 15 to 20 feet along the Texas coast. Let your mind rest with this image for a moment. The ocean rising, pushed by wind and pressure, advancing inland beyond its normal boundaries. There is something both terrifying and awe-inspiring about the ocean's power, about the sheer volume of water that can be moved by atmospheric forces. Yet, from your safe comfortable position. You can observe this phenomenon with curiosity rather than fear, understanding it as part of the natural exchange of energy between ocean and atmosphere. Your breathing continues, slow and steady. Your body is deeply relaxed now, perhaps on the edge of sleep. That is perfectly fine. Let yourself drift. The words will continue, a gentle background, a rhythm like waves on a shore, and whether you hear every word or drift in and out of awareness does not matter. What matters is rest and release and the gentle letting go that leads to sleep. Tropical cyclones do not last forever. Eventually they weaken and dissipate, energy exhausted or their structure disrupted. This can happen in several ways. If a tropical cyclone moves over land, it is cut off from its energy source, the warm ocean water, and friction with the land surface disrupts its circulation. The storm weakens rapidly. It can still produce heavy rain and flooding as it decays. If a tropical cyclone moves over cooler water, it loses its energy source and weakens. This is why tropical cyclones that move into the mid-latitudes, where ocean temperatures are cooler, typically weaken and eventually transition into extratropical cyclones, mid-latitude low-pressure systems with different structure and energy sources. If a tropical cyclone encounters strong wind shear, its circulation can be disrupted, with the upper level and lower level centers becoming displaced from each other. Without the vertical alignment necessary to maintain the warm core structure, the storm weakens. Sometimes, tropical cyclones undergo an eye wall replacement cycle, where a new eye wall forms outside the original one, and the inner eye wall dissipates. During this process, the storm typically weakens temporarily, then may re-intensify once the new eye wall contracts. This cycle can occur multiple times in long-lived, intense tropical cyclones of open water. Despite their destructive potential, tropical cyclones play important roles in the Earth system. They transport heat from the tropics toward the poles, helping to balance the planet's energy budget. They bring rainfall to many regions, sometimes providing a significant portion of annual precipitation. They mix the ocean, bringing cooler water from depth to the surface, which can affect marine ecosystems and global climate patterns. In recent decades, scientists have been studying how tropical cyclones might be changing in response to climate change. The physics suggests that while the total number of tropical cyclones might not increase and might even decrease, proportion of intense storms, Category 4 and 5, is likely to increase as ocean temperatures rise. Additionally, tropical cyclones are likely to produce more rainfall. The warmer atmosphere can hold more water vapor, and there is evidence that tropical cyclones may be moving more slowly, which increases rainfall totals and flooding impacts in affected areas. These are active areas of research, with scientists using historical records, satellite data, and computer models to understand past changes and project future ones. The goal is to improve our ability to predict tropical cyclone behavior and help communities prepare for and adapt to the risks these storms pose. As we conclude this first part of our journey through extreme weather, let us take a moment to reflect on what we have explored. We have seen how the atmosphere, driven by uneven solar heating, creates weather through the movement of air and water. We've watched cumulus clouds grow into thunderstorms, seen lightning bridge the gap between cloud and ground, observed supercells with their rotating updrafts and potential for severe weather. We have travelled to the tropics and witnessed the birth and life of hurricanes, those vast heat engines that dominate the weather of the warm season. All of this, the clouds and storms, the wind and rain, the lightning and thunder, represents the atmosphere in motion, energy being redistributed, the planet seeking balance. And in understanding these processes, we find not just knowledge, but kind of peace, a recognition that we are part of something vast and ancient, something that will continue long after our brief lives have ended. Let yourself rest now in this understanding. Let the weight of your body be fully supported. Let your breathing be soft and natural. Let your thoughts drift like clouds, forming and dissolving, without effort or intention. Soon we will explore tornadoes in detail, examine extreme precipitation and flooding, investigate severe winds and heat extremes, and witness the dissipation and renewal that completes the cycle of extreme weather. But for now, simply rest, simply be, simply allow sleep to come, if it will, in its own time, in its own way. The atmosphere breathes, the ocean breathes, and you breathe, part of the same planetary system, the same exchange of energy and matter that creates all weather, all life, all change. Rest in this connection, rest in this moment, rest. As you settle back into comfort, take a moment to notice your body. Perhaps it feels heavier than when we began, more relaxed, more ready for sleep. Perhaps your mind is quieter, thoughts moving more slowly, like clouds drifting across a summer sky. Whatever you are experiencing is exactly right. There is nowhere to go, nothing to achieve, only this gentle exploration of how air and water create the weather that shapes our world. So far, we have journeyed from the smallest beginnings of weather, the warming of the ground, the rising of air, the formation of clouds, through increasingly dramatic phenomena, thunderstorms, with their lightning and thunder, supercells, with their rotating updrafts, and finally tropical cyclones, those vast spiraling storms that dominate the tropical oceans. We have seen how the atmosphere, driven by energy from the sun and the ocean, organizes itself into patterns of extraordinary power and beauty. Now we will continue this exploration, focusing on some of the most intense and localized extreme weather phenomena, tornadoes, those violently rotating columns of air that represent the atmosphere's most concentrated fury. We will examine extreme precipitation and the flooding it can cause, investigate severe winds and heat extremes, and finally witness the dissipation and renewal that completes the cycle, returning the atmosphere to a state of relative calm. We will approach these topics with the same gentle curiosity we've maintained throughout, understanding that even the most violent weather is simply the atmosphere doing what it must to maintain balance, to redistribute energy, to respond to the forces that shape it. From a sufficient distance, with sufficient understanding, even a tornado becomes not a thing to fear, but a phenomenon to appreciate, a testament to power of rotation, pressure, and wind. Let us begin with tornadoes, those most photogenic and feared of all weather phenomena. A tornado is, in its simplest definition, a violently rotating column of air extending from the base of a thunderstorm to the ground. But this simple definition barely captures the complexity of tornado formation, the variety of tornado types, or the range of intensities these vortices can achieve. Tornadoes occur on every continent except Antarctica, but they are most common in the central United States, in the region sometimes called Tornado Alley, stretching from Texas northward through Oklahoma, Kansas, and Nebraska. This region sees more tornadoes than anywhere else on Earth due to its unique geography and atmospheric patterns. The Rocky Mountains to the west, the Gulf of Mexico to the south, and the relatively flat terrain of the Great Plains create conditions where warm, moist air from the Gulf can collide with cool, dry air from Canada, with the jet stream aloft providing wind shear, all the ingredients necessary for supercell thunderstorms and tornadoes. But what exactly causes a tornado to form? This question has occupied meteorologists for decades, and while we understand the general process, many details remain subjects of active research. What we know is that tornadoes are associated with rotation in thunderstorms, and that this rotation can be concentrated and intensified through various mechanisms until it extends from cloud to ground. The rotation in a supercell thunderstorm, the mesocyclone we discussed in Part 1, is typically several miles in diameter and extends through much of the storm's depth. For a tornado to form, this broad rotation must be concentrated into a much smaller area, perhaps a few hundred yards across, and must extend downward to reach the ground. This concentration and downward extension is called tornadogenesis, and it appears to involve the interaction of the storm's updraft and downdraft in ways that are still not fully understood. One important factor is the rear flank downdraft, a region of descending air on the backside of the supercell, where precipitation is falling and evaporative cooling is occurring. This downdraft can wrap around the mesocyclone, and where it meets the updraft, strong horizontal gradients in temperature and wind can develop. These gradients can generate additional rotation, and this rotation can be tilted into the vertical by the updraft, creating a smaller, more intense vortex. Another factor is the development of low-level mesocyclone, a region of rotation in the lowest few thousand feet of the atmosphere. This low-level rotation can develop independently of the mid-level mesocyclone through processes involving the storm's outflow boundaries and the ambient wind shear. When strong, low-level rotation is present beneath a supercell, the likelihood of tornadogenesis increases significantly. The actual moment of tornado formation is often marked by the appearance of a funnel cloud, a rotating cone of condensed water droplets, extending downward from the cloud base. Initially, this funnel may not reach the ground, but as the rotation intensifies, that extends downward, it eventually makes contact with the surface. At that moment, it becomes a tornado, and debris begins to be lofted into the air, often creating a debris cloud at the base of the funnel that makes the tornado more visible. Not all tornadoes look the same. Some are narrow, rope-like vortices, perhaps only a few yards wide, lasting only a few minutes. Others are massive wedges, wider than they are tall, sometimes more than a mile wide, persisting for an hour or more, and travelling 50 miles or more across the landscape. The appearance of a tornado depends on many factors: the amount of condensation in the funnel, the amount of debris being lofted, the lighting conditions, and the structure of the parent thunderstorm. Some tornadoes are nearly invisible, with little condensation and light debris, appearing as a slight disturbance in the air or a swirl of dust. Others are dark and ominous, filled with debris and backlit by the sun. Still others are wrapped in rain, completely obscured from view, and making them particularly dangerous because people may not realize a tornado is approaching until it is too late. The intensity of tornadoes is rated using the enhanced Fujita scale, which ranges from EF0 to EF5 based on the damage the tornado causes. This is an indirect measure of wind speed, as it is extremely difficult to measure winds directly in a tornado. Most anemometers are destroyed before they can record the strongest winds. The scale is based on damage indicators, what happened to various types of structures and vegetation. An EF0 tornado has winds of 65 to 85 miles per hour and causes minor damage, broken branches, damaged shingles, shallow-rooted trees pushed over. An EF1 tornado has winds of 86 to 110 miles per hour and causes moderate damage, roofs partially removed, windows broken, mobile homes overturned. An EF2 tornado has winds of 111 to 135 miles per hour and causes considerable damage, roofs torn off well-constructed houses, large trees snapped or uprooted, cars lifted off the ground. An EF3 tornado has winds of 136 to 165 miles per hour and causes severe damage, entire stories of well-constructed houses destroyed, severe damage to large buildings, trains overturned. An EF4 tornado has winds of 166 to 200 miles per hour and causes devastating damage, well-constructed houses leveled, structures with weak foundations blown away, cars thrown considerable distances. And an EF5 tornado has winds exceeding 200 miles per hour and causes incredible damage. Strong frame houses lifted off foundations and carried considerable distances, automobile-sized missiles thrown through the air, trees debarked. Incredible phenomena occur. E5 tornadoes are rare. Only a few occur each decade in the United States. But when they do, the destruction is almost total within the core of the damage path. The most violent tornadoes have winds estimated at 250 to 300 miles per hour, or even higher, though these estimates are uncertain because such winds are beyond the range of most damage indicators. Let your mind rest for a moment with the image of a tornado, not with fear, but with a kind of awed respect for the power of rotation, for what happens, and wind begins to spin faster and faster around a central axis. In a way, Tikpo Noto is like a figure skater pulling in their arms to spin faster, or water spiraling down a drain. It is a concentration of rotation, a focusing of the atmosphere's angular momentum into a smaller and smaller space, until the winds reach extraordinary speeds. But you are safe here, observing from a distance, learning about these phenomena without any danger. Let your breathing remain slow and steady. Let your body remain relaxed and heavy. We are simply exploring, simply understanding, and in that understanding, finding a kind of peace. Inside a tornado, the winds spiral inward and upward around a central core. In most intense tornadoes, this core may contain a region of lower pressure, and some tornadoes have been observed to have multiple vortices, smaller whirls rotating around the main circulation, like planets orbiting a sun. These multiple vortex tornadoes can cause particularly erratic damage, with extreme destruction in the paths of the individual vortices and less damage in between. The sound of a tornado is often described as similar to a freight train or a jet engine, a deep, continuous roar created by the wind and by debris being carried and tumbled by the circulation. People who have been very close to tornadoes also report hearing a variety of other sounds: a waterfall-like rushing, a crackling or popping, a high-pitched whistle or scream. These sounds are created by the interaction of wind with structures, vegetation, and debris, and by the turbulence within the tornado itself. The lifespan of a tornado varies greatly. Some last only a few seconds or minutes, touching down briefly and then dissipating. Others persist for an hour or more, traveling 50 miles or more across the landscape. The longest tracked tornado on record occurred on 18th of March, 1925, the Tri-State tornado, which traveled 219 miles across Missouri, Illinois, and Indiana, lasting about 3.5 hours and killing nearly 700 people. This tornado was likely a family of tornadoes, multiple tornadoes produced by the same supercell in succession. But the continuous damage path suggests extraordinary persistence. Most tornadoes move from southwest to northeast, following the motion of their parent thunderstorm at speeds typically between 30 and 50 miles per hour. However, tornadoes can move in any direction, and their motion can be erratic, with sudden changes in direction or speed. This unpredictability is one reason tornadoes are so dangerous. It is difficult to know exactly where a tornado will go, even with modern radar and forecasting techniques. Tornado forecasting has improved dramatically over the past few decades, thanks to advances in radar technology, computer modeling, and understanding of storm processes. Doppler radar, which can detect motion toward and away from the radar, allows meteorologists to identify rotation within thunderstorms, often before a tornado forms. When rotation is detected, a tornado warning can be issued, giving people in the path precious minutes to seek shelter. But despite these advances, tornadoes remain difficult to predict with precision. We can identify conditions favorable for tornadoes and can issue watches covering large areas for several hours. We can detect rotation in thunderstorms and issue warnings for specific counties or portions of counties. But we cannot yet predict exactly where and when a tornado will touch down, how strong it will be, or exactly what path it will take. This uncertainty is inherent in the chaotic nature of the atmosphere, where small differences in initial conditions can lead to large differences in outcomes. Let us pause here and simply breathe. In and out, slowly, naturally. The tornadoes we've been discussing are powerful and dangerous, yes, but they are also rare. Most thunderstorms do not produce tornadoes. Most days, even in Tornado Alley, are tornado-free, and even when tornadoes do occur, they affect only a tiny fraction of the landscape, a path perhaps a few hundred yards wide and a few miles long, in a country spanning millions of square miles. This perspective does not diminish the tragedy when tornadoes do strike populated areas, but it reminds us that extreme weather, while dramatic and newsworthy, is the exception rather than the rule. Most weather is ordinary, gentle breezes, light rain, fair skies. The atmosphere spends most of its time in relatively calm states, with extreme events punctuating the calm, like exclamation points in a long, quiet sentence. Your eyelids are growing heavier now, perhaps. Your thoughts are slowing, becoming less distinct. This is good. This is the natural progression towards sleep. Let it happen. Let yourself drift. The words will continue, a gentle background, and whether you hear them or not does not matter. What matters is rest. Let us shift our attention now from tornadoes to another form of extreme weather, extreme precipitation, and the flooding it can cause. Water is essential to life, and rain is generally welcome, replenishing soil moisture, filling reservoirs, sustaining ecosystems. But too much rain, falling too quickly, or persisting too long, can transform from blessing to disaster. Extreme precipitation events are those that produce rainfall amounts far exceeding the normal or expected values for a given location and time period. What constitutes extreme varies by location. An inch of rain in an hour might be unremarkable in the tropics, but extraordinary in an arid region. Meteorologists often define extreme precipitation in terms of return periods. A 100-year rainfall event is one that has a 1% chance of occurring in any given year based on historical records. But these return periods are statistical constructs, not guarantees. A 100-year event can occur 2 years in a row, or not at all for centuries. And there is evidence that extreme precipitation events are becoming more frequent and more intense in many parts of the world, likely due to climate change. A warmer atmosphere can hold more water vapor, about 7% more for each degree Celsius of warming, which means more water is available to fall as precipitation when conditions are right. Extreme precipitation can result from various meteorological situations. Slow-moving or stationary thunderstorms can produce tremendous rainfall totals in a small area, sometimes leading to flash flooding. Training thunderstorms, where successive storms move over the same area, like cars on a train track, can produce even higher totals. Tropical cyclones, as we discussed in Part 1, can produce extreme rainfall, sometimes dropping more than 20 inches in the day. And atmospheric rivers, long, narrow corridors of concentrated water vapor in the atmosphere, can produce days of heavy rain when they make landfall, particularly along mountainous coastlines. Flash flooding occurs when rainfall exceeds the capacity of the ground to absorb it and the capacity of streams and rivers to carry it away. Water accumulates rapidly, sometimes in minutes, turning streets into rivers, filling low-lying areas, and creating dangerous currents. Flash floods are particularly dangerous because they occur with little warning and because people often underestimate the power of moving water. Just 6 inches of fast-moving water can knock a person off their feet, and 2 feet can carry away most vehicles. River flooding occurs when prolonged or repeated rainfall causes rivers to exceed their banks. Unlike flash flooding, river flooding typically develops over days or weeks as rainfall accumulates in a watershed and flows downstream. Major river floods can inundate vast areas, persisting for weeks, causing billions of dollars in damage and displacing thousands or millions of people. The Great Flood of 1993, which affected the Mississippi and Missouri River basins, was caused by persistent heavy rainfall throughout the spring and summer. Some areas received double their normal rainfall for the period. Rivers remained above flood stage for months, with some locations experiencing record crests. 50 people died, and economic losses exceeded $30 billion. Entire towns were inundated, crops were destroyed, and transportation networks were disrupted. More recently, in August 2016, a slow-moving area of low pressure produced extreme rainfall in southern Louisiana, with some locations receiving more than 30 inches of rain in a few days. The resulting flooding damaged or destroyed more than 140,000 homes and killed 13 people. This event was particularly notable because it occurred in an area not typically associated with extreme flooding, and because it developed without a tropical cyclone or other obvious large-scale weather system. Urban areas are particularly vulnerable to flooding because impervious surfaces, pavement, buildings, parking lots, prevent water from soaking into the ground. Instead, water runs off rapidly into storm drains and streams, which can quickly become overwhelmed during heavy rainfall. Urban flooding can occur even from relatively modest rainfall amounts if the intensity is high enough to exceed drainage capacity. Coastal flooding can result from storm surge, as we discussed with tropical cyclones, but also from high tides, waves, and sea level rise. As global sea levels rise due to climate change, from ephemeral expansion of warming ocean water, and from melting ice sheets and glaciers, coastal areas are becoming more vulnerable to flooding, even without storms. What was once a rare extreme high tide may become a regular occurrence, inundating streets and overwhelming drainage systems. Let your mind rest with the image of water, not as a threat, but as a fundamental part of Earth's system. Water cycles endlessly, evaporating from oceans, lakes, and land, condensing into clouds, falling as precipitation, flowing in streams and rivers back to the ocean. This cycle has operated for billions of years, shaping landscapes, sustaining life, connecting the atmosphere, land, and ocean in an intricate dance. Sometimes this dance becomes intense, with too much water in the wrong place at the wrong time. Even flooding, destructive as it can be, plays roles in natural systems. Floodplains are among the most fertile agricultural lands because periodic flooding deposits nutrient-rich sediment. Eggplants, which are essentially areas that flood regularly, are among the most productive ecosystems on Earth, providing habitat for countless species and filtering water naturally. Your breathing continues, slow and rhythmic, like waves lapping at a shore, in and out, effortlessly, naturally. Your body is deeply relaxed now, perhaps barely aware of its own weight and position. This is the threshold of sleep, this quiet, drifting state where awareness becomes soft and diffuse. Let us continue our journey, moving now to severe winds, those powerful straight-line winds that can rival tornadoes in their destructive potential, though they lack the rotation that defines a tornado. Severe winds can be produced by various weather phenomena. Downbursts are strong downdrafts that hit the ground and spread out horizontally, creating winds that can exceed 100 miles per h.h. in most intense cases. These are called microbursts if they affect an area less than 2.5 miles across, or macrobursts if they affect a larger area. Downbursts are particularly dangerous to aircraft during takeoff and landing, as the sudden wind shear can cause loss of lift. Derechos are widespread, long-lived windstorms associated with fast-moving bands of thunderstorms. The term comes from a Spanish word meaning straight ahead, distinguishing these straight-line wind events from tornadoes. To be classified as a derecho, the wind damage must extend more than 250 miles, with wind gusts of at least 58 miles per h.h. along most of the length. Derechos can last for many hours and travel more than 1,000 miles, leaving a swath of damage resembling that of a tornado outbreak, but caused by straight-line winds rather than rotation. One of the most notable dereches in recent years occurred on 10th August 2020, crossing Iowa and parts of neighboring states. This Midwest derecho produced wind gusts exceeding 100 miles per hour in some locations, flattening millions of acres of crops, damaging or destroying thousands of homes and buildings, and leaving hundreds of thousands without power for days. The damage was so extensive that it was visible from satellite, with the affected area appearing darker due to the loss of vegetation. Terekvos form when a line of thunderstorms develops a particularly strong and persistent cold pool, a region of cool air at the surface, created by evaporative cooling and by downdrafts bringing cooler air from aloft. This cold pool acts like a wedge, lifting warm, moist air ahead of it and maintaining the line of storms. The leading edge of the cold pool, called the gust front, can produce winds of 70 to 100 miles per hour or more, especially when the storms are moving rapidly. Another source of severe winds is the downslope windstorm, which occurs when strong winds blow perpendicular to a mountain range. As air is forced over the mountains, it can accelerate dramatically on the downwind side, producing winds that can exceed 100 miles per hour in valleys and at the base of the mountains. These winds are known by various local names: Chinook winds in the Rockies, Santa Ana winds in Southern California, Foehn winds in the Alps. Downslope windstorms can cause rapid temperature changes. As the descending air warms by compression, temperature increases of 20 to 40 degrees Fahrenheit in a few hours are not uncommon. These winds can also be extremely dry, as the air has lost its moisture on the upwind side of the mountains, leading to very low relative humidity on the downwind side. This combination of strong winds, warm temperatures, and low humidity creates extreme fire danger, and many of the most destructive wildfires have occurred during downslope wind events. The Santa Ana winds of Southern California are particularly notorious for their role in wildfires. These winds blow from the desert interior toward the coast, typically in fall and winter, bringing hot, dry air and gusts that can exceed 70 miles per hour. During Santa Ana events, relative humidity can drop below 10%, and any fire that starts can spread rapidly, driven by the wind and fueled by dry vegetation. The 2003 Cedar Fire, the 2007 Witch Fire, and the 2018 Camp Fire all occurred during periods of strong offshore winds. Let us pause again, settling into the quiet space between thoughts. The winds we have been discussing are powerful, yes, but wind is also gentle. The breeze that cools on a hot day, the rustle of leaves, the whisper through grass. Wind is simply air in motion, responding to pressure differences, seeking balance. Sometimes that motion is gentle, sometimes fierce, but always it is the atmosphere doing what it must. Your mind is quieter now, thoughts fewer and farther between. This is the natural progression towards sleep, this gradual quieting, this gentle letting go. There was no need to hold on to awareness, no need to follow every word. Simply rest, simply be. Let us turn our attention now to heat extremes, those periods when temperature rises far above normal, creating conditions that can be not just uncomfortable, but dangerous to human health and to ecosystems. Heat waves are prolonged periods of excessively hot weather, typically defined relative to local climate norms. What constitutes a heat wave varies by location. 95 degrees Fahrenheit might be unremarkable in Phoenix, but would be an extreme heat wave in Seattle. The key is that temperatures are significantly above what is normal for that location and time of year, and that the heat persists for several days or longer. Heat waves form when a persistent high-pressure system becomes established over a region. High pressure is associated with sinking air, and sinking air warms by compression. This sinking motion also suppresses cloud formation, allowing strong sunshine to heat the ground. which in turn heats the air near the surface. The result is a feedback loop. High pressure causes clear skies, and sinking air, which causes heating, which strengthens the high pressure, which causes more heating. These persistent high-pressure systems, sometimes called heat domes, can remain in place for days or weeks, particularly when the larger-scale atmospheric flow becomes blocked, meaning usual west-to-east progression of weather systems stalls and patterns become locked in place. During such blocking patterns, the same areas experience the same weather day after day. Heat under the high pressure and often cool, wet weather in adjacent areas under low pressure. In cases of heat waves can be severe, particularly for vulnerable populations, the elderly, the very young, people with chronic health conditions, and those without access to air conditioning. Heat stress occurs when the body cannot cool itself effectively through sweating and other mechanisms. When air temperature exceeds skin temperature, the body gains heat from the environment rather than losing it. When humidity is high, sweat does not evaporate efficiently, reducing the body's ability to cool itself. The combination of heat and humidity is measured by the heat index, which represents what the temperature feels like to the human body. A heat index above 105 degrees Fahrenheit is considered dangerous, with heat exhaustion and heat stroke becoming likely with prolonged exposure or physical activity. A heat index above 130 degrees Fahrenheit is considered extremely dangerous, with heat stroke highly likely. The deadliest heatwave in recent U.S. history occurred in July 1995 in Chicago, where temperatures exceeded 100 degrees Fahrenheit for several days, with heat indices reaching 120 degrees Fahrenheit or higher. More than 700 people died, most of them elderly residents of the city without air conditioning. This event highlighted the vulnerability of urban populations to extreme heat and led to changes in how cities prepare for and respond to heat waves. More recently, the Pacific Northwest heat wave of June 2021 shattered temperature records across a region unaccustomed to extreme heat. Portland, Oregon, reached 116 degrees Fahrenheit. Seattle reached 108 degrees Fahrenheit, and Lytton, British Columbia, reached 121 degrees Fahrenheit, the highest temperature ever recorded in Canada. Hundreds of people died, and the heat, combined with dry conditions, contributed to devastating wildfires. This event was particularly notable because it occurred in a region where most homes lack air conditioning, as extreme heat has historically been rare. It was also notable for the magnitude of the records broken, not by a degree or two, but by 5 to 10 degrees or more, suggesting that climate change is pushing temperatures into ranges that have no precedent in the historical record, even vulnerable to heat, because of the urban heat island effect. Cities are typically several degrees warmer than surrounding rural areas, especially at night, due to the thermal properties of buildings and pavement, the lack of vegetation, and the waste heat from human activities. During heat waves, this urban heat island effect is amplified, and nighttime temperatures may remain in the 80s or 90s Fahrenheit, preventing people from cooling off and recovering from daytime heat stress. Heat waves also have broader impacts beyond human health. They stress ecosystems, causing drought stress in plants, increasing wildfire risk, and affecting wildlife. They increase energy demand for cooling, sometimes straining electrical grids to the point of failure. They can damage infrastructure, as roads and runways can buckle, Rail lines can warp, and power lines can sag, and they can affect agriculture, reducing crop yields or causing crop failures if heat coincides with critical growth stages. There is strong evidence that heat waves are becoming more frequent, more intense, and longer lasting due to climate change. As global average temperatures rise, the entire distribution of temperatures shifts toward warmer values, making extreme heat more likely. What was once a rare extreme event becomes more common, and new extremes, beyond anything in the historical record, become possible. Let your awareness rest with the image of heat, not oppressive heat, but gentle warmth. The warmth of sunshine on your skin, the warmth of a comfortable bed, the warmth of your own body maintaining its perfect temperature without any conscious effort on your part. Your body knows how to regulate temperature, how to maintain balance, how to keep you safe and comfortable. Trust in this wisdom. Trust in this process. Your breathing is very slow now, very soft. Perhaps you are barely aware of it, barely aware of anything except a gentle, floating sensation. This is sleep approaching. This is consciousness releasing its grip. This is the natural transition from waking to dreaming to deep, restorative rest. Let us move towards the completion of our journey. Now, exploring the dissipation and renewal that follows extreme weather, return to calm, the restoration of balance, the atmosphere's way of resetting itself after intense activity. Every storm eventually ends. Every heat wave eventually breaks. Every period of extreme weather gives way to more typical conditions. This is because the processes that create extreme weather are self-limiting. To consume the energy had instability that fuel them, and in doing so, they restore balance to the atmosphere. A thunderstorm dissipates when its updraft weakens and can no longer sustain itself. This happens when the storm's cold outflow cuts off the supply of warm, moist inflow air, or when the instability in the atmosphere is exhausted, or when the storm moves into an environment less favorable for convection. As the updraft weakens, precipitation decreases, lightning becomes less frequent, and cloud begins to dissipate. The anvil may persist for hours, gradually spreading and thinning, but the active storm is over. A tornado dissipates when the processes that maintain it cease. This might happen when the rear flank downdraft becomes too strong, wrapping completely around the tornado and cutting off its inflow. It might happen when the parent thunderstorm weakens, or when the low-level mesocyclone dissipates. As the tornado weakens, it typically becomes narrower, transitioning from a wide wedge to a narrow rope, before finally lifting back into the cloud. The dissipation can be rapid, occurring in just a minute or two, or more gradual, with the tornado weakening and strengthening several times before finally ending. A tropical cyclone dissipates when it loses its energy source, or when its structure is disrupted, moving over land or cool water, cuts off the supply of warm, moist air that fuels the storm. Encountering strong wind shear disrupts the storm's circulation. As the storm weakens, its winds decrease, its eye fills in, and its spiral structure becomes less organized. Eventually, it degenerates into a remnant low-pressure system, perhaps still producing rain, but no longer having the organized structure of a tropical cyclone. A heat wave breaks when the persistent high-pressure system finally moves or weakens, allowing cooler air to move in. This often happens when the larger-scale atmospheric pattern changes, ending the blocking that kept the high pressure in place. The transition can be gradual, with temperatures slowly moderating over several days, or abrupt, with a cold front bringing a sudden end to the heat and perhaps triggering thunderstorms as the contrasting air masses collide. After extreme weather passes, there is often a period of unusual calm and clarity. After a thunderstorm, the air is cooler and fresher, washed clean of dust and pollutants. The sky may be exceptionally clear, with visibility extending for miles. After a tropical cyclone, once the winds subside and the rain ends, there may be a period of beautiful weather, with clear skies and light winds, before the next weather system approaches. After a heat wave breaks, the relief is palpable, with temperatures returning to comfortable levels and humidity decreasing. This post-storm calm is more than just pleasant. It represents the atmosphere having achieved, at least temporarily, a more balanced state. The energy that was concentrated in the storm has been redistributed. The instability that fueled convection has been released. The temperature contrasts that drove the circulation have been reduced. The atmosphere has done its work, and now it rests, gathering energy for the next cycle. But the atmosphere never rests completely. Even in the calmest conditions, processes are at work that will eventually lead to new weather. The sun continues to heat the ground unevenly. Water continues to evaporate from oceans and land. Air masses with different properties continue to move and interact. Slowly, gradually, the ingredients for new weather accumulate, and the cycle begins again. This cycle, from calm to storm to calm again, is fundamental to Earth's climate system. It is how the atmosphere transports heat from the equator towards the poles, how it distributes moisture from oceans to land, how it maintains the conditions that make life possible. Without this cycle, without weather, in all its forms from gentle to extreme, Earth would be a very different planet, perhaps not habitable at all. Let us rest here for a long moment, in this understanding of cycles, of balance, of the atmosphere's endless work to maintain equilibrium. Your own body operates in cycles, breathing in and out, heart beating, blood circulating, cells renewing themselves. You are, in a sense, a small weather system, maintaining your own internal climate, responding to changes, seeking balance. And just as the atmosphere cycles between activity and rest, so do you. You have been awake, active, engaged with the world. Now you are moving toward rest, toward sleep, toward the renewal that comes with letting go of consciousness for a time. This is natural. This is necessary. This is good. Hold this quiet space now. Let the silence extend. There is no need for more words, no need for more information. Simply rest in the knowledge that you have journeyed through the atmosphere's most powerful expressions, from the gentlest cloud to the fiercest tornado, from the first drops of rain to the most devastating flood, from the cooling breeze to the scorching heat wave. You have witnessed the full spectrum of weather, and in doing so, perhaps you found a deeper appreciation for the atmosphere that surrounds and sustains us. The atmosphere is always there, always working, always seeking balance. It asks nothing of us except that we respect its power and adapt to its changes. And in return, it gives us everything: the air we breathe, the water we drink, the climate that makes life possible, and the weather that, in all its variety, makes each day unique. As we conclude this journey, let us take a few moments to simply be present with the atmosphere, to feel the air around us, to notice our breathing, to appreciate the invisible ocean in which we live. The air is touching your skin right now, supporting you, surrounding you. It is the same air that forms clouds and storms, the same air that carries rain and snow, the same air that has been cycling through the atmosphere for billions of years. You are breathing air that has been breathed by countless others, by people who lived centuries ago, by animals in distant lands, by plants that converted carbon dioxide to oxygen. You are part of an ancient cycle, connected to all life, all weather, all the processes that make Earth a living planet. Let this connection bring you peace. Let this understanding bring you calm. Let this knowledge that you are part of something vast and enduring help you release the small worries, tensions of the day. Your body is completely relaxed now, completely at ease. Your mind is quiet, thoughts airily forming before dissolving like morning mist. You are on the very edge of sleep, that threshold between waking and dreaming, between consciousness and the deep rest that renews body and mind. Let yourself cross that threshold now. Let yourself drift into sleep, into dreams, into the darkness that is not empty, but full of rest and renewal. The atmosphere will continue its work while you sleep, clouds forming, anticipating, winds blowing, rain falling somewhere, sunshine warming somewhere else. The great cycles will continue as they always have, as they always will. And you will sleep and rest and wake renewed, ready to experience another day under the sky, another day of weather in all its forms, another day of being alive on this remarkable planet with its remarkable atmosphere. Sleep now, rest now. Let go now. The journey is complete. The exploration is finished. The understanding has been gained. Now there is only rest, only peace, only the gentle darkness of sleep. Breathe slowly, breathe softly, breathe naturally, and sleep. If you have found this journey through extreme weather helpful, if these explorations of atmospheric science have brought you knowledge or peace, or simply helped you relax towards sleep, consider subscribing to this channel for more science and nature content designed to educate and soothe. Like this video if you would like to see more topics explored in this gentle, sleep-friendly way, and know that the atmosphere is always there, always fascinating, always worthy for wonder and respect. But for now, simply sleep, simply rest, simply be. The atmosphere breathes, the planet breathes, and you breathe, part of it all, connected to it all, safe and at peace. Good night.